Hello, hello, and welcome to this class of quantum mechanics. And the topic which we are going to discuss is the time dependent perturbation theory. As we all came across the time independent perturbation theory for both the cases, that is, for degenerate case and for the non degenerate case, today's topic is something different, that is, the time dependent perturbation theory. Here also, the Hamiltonian can be expressed as h equals to h0 plus lambda h prime. So we can write that h equals to h0 plus lambda h prime. So this is the Hamiltonian. If the Hamiltonian can be written by this manner, that is, where the Hamiltonian, total Hamiltonian h equals to h0 plus lambda h prime, where h0 is the time independent unperturbed Hamiltonian. Be careful that here h0 is the time independent unperturbed Hamiltonian, while the part lambda h prime, is a small time dependent perturbation. Why it is small? Since lambda is very less than 1. Now it is a dimensionless and a real quantity. So lambda is a real dimensionless quantity and its value should be very less than 1. It actually arises due to the interaction of external agency with the system under consideration. Now, I can discuss you an example about this, that interaction of electromagnetic radiation with the atom may be an example of this system. So, here the perturbation is time dependent, that is, the time behavior of wave functions of the perturbed system can be determined by solving the time dependent Schrodinger equation. And we can write that h psi is obviously a function of r and t, that h psi is equals to Hamiltonian becomes h0 plus lambda. So we can write, this 0 can be written is here as the prefix. So h0 plus lambda h prime and then psi rt. And that is equals to, as we know that for the time dependent Schrodinger equation, it is equals to IH cut del psi del t. Here also psi is a function of RT. Now, like in the time independent case, let us express the perturbed wave function psi RT as an expansion in the wave function psi n0 of the unperturbed time dependent Schrodinger equation. That is we can write psi rt equals to summation over n a n t psi n 0 a n t psi n 0, and here also psi n is function of r and t, or we can write it as summation over n, this is a n t, then psi n0 is expanded by writing phi n0. It is function of the position, that is r, and then comes the time dependent part, that is e to the power minus I en0 t by h cut. Now this equation can be written as equation, let it be equation 2, let this equation be 1, and this is my equation number 3. Now here I have used the time dependence of psi n0 psi n0 rt as phi n0 r into e to the power minus of I en0 t by h cut. That is, here this method of treating time dependent problem is known as method of variation of constants. Now here what we can see that this function psi n0 rt, that is, it is a function of position as well as time, and it is expanded into two functions, or it can be written as a product of two functions where phi n0 r is the positional dependent function and the time dependent function is written as e to the power minus I en0 t by h cut. So this is a method of writing a time dependent function, a time dependent and a position dependent function as a product of two different functions. One is the position dependent function, that is phi n0 r, and the other is the time dependent part, that is e to the power minus I en0 t by h cut. So the phi n0 r describes the states of the unperturbed system at time t equals to 0. So what we can say about that, the term of phi n0 r, it is actually the states of the unperturbed system at time t equals to 0. Now the wave function, as the wave function is taken to be normalized, as the wave function we have taken is always normalized at all times. So we can write that we can write 1 equals to, that is, if the function is normalized, 1 equals to integral psi n star, this is function of rt, or psi n, again function of rt, and d tau. Now psi n star rt, or rather you can write it as psi star. You can write it as the function is taken as psi rt. So the normalized, if the wave function is normalized, it can be written as 1 equals to integral psi star rt into psi rt d tau. And then putting the values, that is summation n dash a n star t, then a n t, and then comes the integral phi n0 star, this is the function of r, then phi n prime 0, it is also function of r, and then comes the time independent part, that is e to the power minus I en0 t by h cut and e to the power minus of I en prime 0 t by h cut, and then d tau. So we can write it as summation over n prime a n star t a n, it is actually n prime t e to the power minus of I en prime 0 t by h cut, or rather you can take t as common, t and divided by h cut, that is e to the power minus I by h cut or it by h cut, en prime 0 minus en 0. then d tau. And then the value should be, and then it will be delta mn, that is the Kronecker delta function delta n prime, delta n prime, and thus the value is equals to summation of mod ant whole square. It is equation 4. Is it clear? Now, since this is a complex conjugate, so it should be plus, and then e to the power, yes, this is all right. This is the value, that is where mod of ant square, can be interpreted as, where mod of an square or mod of ant square can be interpreted as the probability of finding the system in the nth state at time t. So let's move on. Now the Schrodinger equation for the unperturbed Hamiltonian H0, the Schrodinger equation for the unperturbed Hamiltonian H0 for the nth quantum state, can be given as so the Schrodinger equation for the unperturbed Hamiltonian, that is H0 psi n0. This is the unperturbed Hamiltonian H0 psi n0 RT is equals to IH cut del psi n0 del T. Now here I am skipping of writing RT function of psi n0. Actually, this is also a function of R and T. Now, going on, proceeding in this manner, I will not write R and T for the function or for the wave function psi n or an. So just make it sure that it is also a function of R and T. Now this is, let it be equation 5a. Let it be equation 5a. Similarly, phi n0 r, as we know that phi n0 is a function of r. Similarly, phi n0 r and en0 denote the eigenfunction and eigenvalues respectively of the time independent Hamiltonian, that is H0, phi n0. Now this is the function of r, and the eigenvalue, energy eigenvalue, is en0 phi n0 r, and let it be equation 5b. Now let's substitute the value of psi. Let's substitute the value of psi, what I have written in equation 3, into equation 2. So after substituting the value of equation 3 into equation 2, actually the value of equation 3 was the value of psi RT, and equation 2 is the time dependent Schrodinger equation H psi t. So it was H0 plus lambda H prime psi RT. Now that is H0 plus lambda H prime and then psi RT. So substituting the value of psi RT from equation 3, that is summation of an t, it was a function of time, so summation of an t phi n0 e to the power minus of I en0 t by h cut. It was en0 t by h cut. So it was the value of psi RT, and after substituting it into the left hand side of equation 2, we get this. And now in the right hand side of the equation of equation 2, that was IH cut del psi del t. So IH cut and then del t of psi, that is summation ANT phi n0 e to the power minus I en0 t by h cut. So after substituting equation 3 into equation 2, this is the form. Now using the value in equation 5b, that is H0 phi n0. So here in the left hand side of this equation, we have H0 phi n0. So from equation 5b, we can write it as H0 phi n0 equals to En0 phi n0. So after putting that, we get H0 phi n0 equals to En0 phi n0, and here in the right hand side, we have also, let us differentiate this to get the right hand side, and it will be summation ANT now phi n0 and differentiating e to the power minus I en0 t by h cut. So it will become minus I en0 by h cut, then e to the power minus I en0 t by h cut. This is this is the term, and then after ANT differentiating AN, it will become AN dot. It will become AN dot. So again the second term will be plus IH cut del t of, and then the second term, that is IH cut summation of AN dot t phi n0 e to the power minus I en0 t by h cut. So these are the two terms. Now you can see that from the left hand side, if we are substituting the value of H0 phi n0 from equation 5b, this equation can be written as, or the left hand side of this equation can be written as summation ANT En0 phi n0. Now here the En0 phi n0 e to the power minus I en0 t by h cut. Now here the first term will be minus I and I, that is minus of I square. I square means minus 1, so minus of I square means again plus. So it will be summation in t phi n0 en0 e to the power minus I en0 t by h cut. So using this relation we can cancel the term summation of a n t en0 phi n0 e to the power minus I en0 t by h cut on both the sides. And then we actually left with, the term on the left hand side, it will be IH cut. The left hand side we have summation n a n t. This is lambda h prime, so this is lambda h prime phi n0 e to the power minus I en0 t by h cut. So this is the term left in the left hand side of equation, and the term remains in the right hand side will be IH cut summation an dot summation of n dot t phi n0 e to the power minus I en0 t by h cut. I think all of you get it. I'm trying to explain all the steps, trying to derive all the steps of this theory. Now, this theory you can find it in any standard book of quantum mechanics. You can find it in Ghotok, as well as you can find it in Aruldas. So this is the equation, that is in the left hand side it is summation of n t lambda h prime phi n0 e to the power minus of I en0 t by h cut, that equals to IH cut summation over n dot t phi n0 e to the power minus I en0 t by h cut. Now proceeding in the same manner as we have used in the time independent perturbation theory, that is here we are also multiplying this above this equation by phi f0 star from the left, phi f0 star from the left, and integrating it over the entire space. And then what we have to do, that we are going to use the orthonormality condition or the orthonormality property of the eigenfunctions phi n0. So we get, that is I am writing from the taking the right hand side term first, that is IH cut summation over n an dot t, and then as we are multiplying this equation with phi f0 star, so this will be delta fn, then e to the power minus I en0 t by h cut. So this is the term. I am writing it first from the right hand side term, and then the left hand side term becomes summation over n an t lambda h prime. Now this was lambda h prime. Now it will be lambda h prime fn e to the power minus I en0 t by h cut. Let it be equation 6a, where h prime, where h fn prime, or where h prime fn is actually the integral value of phi f star, phi f0 star, h prime rt, phi n0 d tau. So this is actually h prime fn. This particular term we have already used in our previous two video or the previous two classes in the time independent part, that is for the degenerate case as well as for the non-degenerate case. So I think it will not bother you at all. So we have equation 6a. Now, those who are in my class right now, is it okay? May I proceed further? Please have a comment here. Okay, Papri, Orpita, Utpal. Now I have selected this time for the class as because I thought that all of you will be available at this period of time, but only 9 students are in this class. So okay, so let's proceed. Now, using, as usually, now we are going to use the definition of Kronecker delta function. So this equation 6a leads to, now for f equals to n, as because the Kronecker delta is about fn, so for delta fn, for f equals to n, as we know that the Kronecker delta function will be 1. So equation 6a, using the Kronecker definition of Kronecker delta function, equation 6a takes the form, equation 6a takes the form that is ih cut summation over n, a n dot t, and then delta fn becomes 1. So it will be a f dot t, and the summation will also omitted. So by using this definition of Kronecker delta for f equals to n, actually we can find the value of a f dot t from equation 6a, and it will be a f dot t equals to 1 by ih cut, that is 1 by ih cut summation of n a n t lambda h prime, as here h prime fn, e to the power minus of I en0 t by h cut, and from the left hand side the term was e to the power minus I en0 t by h cut, so it will be here, that is e to the power minus I en0 t by h cut, and then here actually, as we are putting the value of f equals to n, so it will be ef0 t by h cut, and then after simplifying this, we can take the denominator, that is 1 by ih cut summation over n ant lambda h prime fn, and then from the denominator side it will be e to the power minus of I, e to the power, as I've taken I common, it will be I ef0 minus en0 t, and then by h cut. So it can be written as e to the power I ef0 minus en0 t by h cut. Now this value ef0 minus en0 by h cut, it can be written as omega. It can be written as omega fn. So writing omega fn equals to ef0 minus en0 by h cut. Writing this omega fn equals to ef0 minus en0 by h cut, this equation af dot t, it becomes 1 by ih cut summation over n t lambda h fn prime, and this is e to the power I omega fn t. So it is e to the power I omega fn t, and let it be equation 6b. So this omega fn, that is ef0 minus en0 by h cut, it actually denotes the Bohr's frequency of transition corresponding to the pair of unperturbed levels ef0 and en0. It is the Bohr's frequency of transition corresponding to the pair of unperturbed levels ef0 and en0. Now the set of equations, that is equation 6a and equation 6b, enables us to determine the time dependence of the coefficients a f dot t, and consequently dependence of wave function on time, and hence the set is completely equivalent to the Schrodinger equation as written in equation 2. Now since as at the initial state of this theorem, I told you that lambda h prime is a very small quantity, as because lambda is very less than 1, so lambda h prime is a very small quantity. So it is reasonable to express AFT as a power series in lambda. So we are writing AFT equals to AF0 is a function of t plus lambda AF1 t, that is function of t plus lambda square AF2 function of t, and so on. This is equation 7. So substituting the values of AFT and ANT from the above equation into equation 6b, and then we have to equate the coefficients of lambda prime on both sides of the resulting equation. We get what we get. So let's find out. Now, as we are writing from equation 7 that we are actually expanding the value of AFT. So now here also expanding the equation 6b, what we found that for r equals to 0, for r equals to 0, af dot af dot t, af dot 0 t is actually 0. Let it be equation 8a for r equals to 0, as because aft equals to this, and from this if we differentiate aft, that is if we find af dot t, it will be af dot 0 t plus lambda af dot 1 t and so on. So af dot 0 t is actually 0. Now for r equals to, next for r equals to 1, by putting r equals to 1, af dot 1, af dot 1, it will be 1 by ih cut, that is ih cut whole to the power minus 1, it can be written as, and then ant, so ant, it becomes an0 lambda, so it can be written as 1 by ih cut summation over an0, it is a function of time, that is an0 t, h prime fn, h prime fn, e to the power j, no, e to the power I omega fn t. So it is equation 8b. Now proceeding for r equals to 2, then af dot 2 function of t, it is also 1 by ih cut summation an1 t h prime fn e to the power I omega fn t. So now this can be written as equation 8c. Now what we have found from these three equations, from the relation 8a, we can conclude that as af dot 0 t equals to 0, it means af0 or af0 t is a constant. So from equation 8a, we conclude that af0, which is a function of time, af0 is actually a constant, as because af dot 0 t equals to 0. So from 8a, we conclude that af0 is a constant. af0 t is a constant. Or in other words, it can be, as you can tell, that af0 t equals to constant means that af0 t does not depend upon time, or it can be written as af0 t is actually equals to af0 time t equals to 0. Now as at t equals to 0, when the perturbation has not yet had a chance to act, at time t equals to 0, the perturbation is not yet have a chance to act. So af1t, af2t, or rather the higher order terms of af1, af2 and all must necessarily be 0. So accordingly from equation 7, accordingly as in equation 7, I have written aft equals to af0 t plus lambda f1 t plus lambda square f2 t and so on. So from equation 7 and from this equation, that is from equation 9, we can tell that af0 is actually af0 0, that is from equation 7 and from equation 9. See carefully that we can write that AF0, that is at time t equals to 0, that is actually AF0 time t equals to 0. So this can be written as equation 9a. I think all you have get it. Please mention or comment here if it is okay. Okay, fine. Now let's continue our discussion. So this is the discussion about the unperturbed part, that is at time t equals to 0, when the perturbation has not yet started. Now what will happen if the perturbation starts? That is, let's discuss about the first order perturbation or the first solution in lambda, that is lambda. So after using this equation 9, equation B, from equation B, so after using equation 9 from equation 8b, as because 8b is actually for r equals to 1, so by using this equation 9 from equation 8b, we have find that AF dot 1t equals to 1 by IH cut N0t. Now by using equation 9, I can write it as N0 time t equals to 0, that is N0 0 H prime Fn e to the power I omega Fn t. So equation 8b can be written as AF dot 1 t equals to 1 by IH cut summation of an0 and then the function time t, it can be written as here also 0, as because from equation 9 you can see that. So it will be an0 0 H prime Fn and e to the power I omega Fn t. So by using equation 9, equation 8b can be written as in this manner. And here we are going to discuss about the first order perturbation. Now, in many practical applications or practical phenomena, the initial conditions are such that at t equals to 0, what does it mean at t equals to 0? That is when the perturbation is not yet applied or turned on, or the radiation yet to arrive. That is, the system is described by one of the unperturbed eigenfunctions, that is, say, phi f0. Now this would mean that our initial conditions are AF00 equals to delta ft, that is AF00 equals to delta f say L, delta FL. So if L not equals to F, if L not equals to F, it means AF00 equals to 0, as the system is in the state phi L0 at t equals to 0. Actually, mod of AF0, mod of AF0 square is the probability that the system is found in the fth state at t equals to 0. Now, let it be equation 9b, and this equation, that is f dot 1t, let it be equation 10. So, making use of these equations, equation 10 results in AF dot 1t, f dot 1t equals to 1 by IH cut summation, as f0 0 becomes delta FL. So n00, it can be written as delta NL. Okay, so it is delta NL H prime Fn e to the power I omega Fn t. Now again using the definition of Kronecker delta function, we can get f dot 1t equals to 1 by IH prime. Now if n equals to L, it means delta NL becomes 1, and H prime Fn can be written as H prime FL. So AF dot 1t, it can be written as 1 by IH cut. The summation term will vanishes, so it will become H prime FL, as because for n equals to L, we are applying the value n equals to L, e to the power I omega FL t. It will be e to the power I omega FL t. Hence, after this, that is, if we are going to find out the value of AF1t, as because now we are actually finding the first order perturbation. So from this equation F dot 1t, we can easily find out the value of AF1. So by integrating this equation, we can find AF1t, and it will be 1 by IH prime integral 0 to t H prime FL e to the power I omega FL t dt, and then an integration constant, let it be C1. So this is the integration constant. So F1t can be written as, now this what will be the value of, we have to find out the value of this integration constant C1. Now by putting the initial condition, that is AF10, that is at t equals to 0. Now putting the value of t equals to 0 here, we can find out that AF10 is actually equals to 0. So as because there will be no perturbation when time t equals to 0, as I have discussed earlier. So it will make the value of that integration constant C1 equals to 0. So by putting the value of the constant C1 equals to 0, we find that AF1t is actually 1 by IH cut integral 0 to t H prime FL e to the power I omega FL t dt, and let it be equation 11. Now, which is the basis for the first order time dependent perturbation theory. So this is all about my time dependent perturbation theory. I have discussed here what I have discussed here. First of all, I have discussed the zeroth order perturbation, that is when the perturbation is not yet arrived, and then after that we actually expanded this discussion to derive the first order perturbation term. Now you can ask me that what's about the second order perturbation. Actually, in this derivation of time dependent perturbation theory, that the value of lambda is so small, that is for the second order perturbation it actually diminishes. So we are neglecting the second order perturbation here. We are only interested to discuss the zeroth order perturbation, that is whenever the perturbation is not yet arrived, and after that the first order perturbation. So this is all about the time dependent perturbation theory. Okay, so goodbye.